Good afternoon and good evening to those of you in Europe, and good morning to those of you in Australia. Welcome to session 5 of the ESIG 2021 Spring Technical Workshop. We have another great session lined up for today, looking at what's going on in the wonderful world of planning. I'm Charlie Smith, the Executive Director of ESIG, and I will provide a few brief opening remarks. As you know, our spring workshop sessions are all being held online and are open to everyone. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julia Matoivasan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who really make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I'd like to ask you to note that the webinar will be 90 minutes long. We had a lot of feedback that our 1-hour workshop sessions were too rushed, so we're experimenting with some longer formats for the spring workshop. Our revised format today will have 3 individual presentations of approximately 20 minutes each in the first hour, followed by 20 to 30 minutes of Q&A after the last speaker. As we are doing with all our webinars now, we'll be using the Slido platform for managing the Q&A, not the WebEx platform. You should go to slido.com on your device and enter ESIG16, ESIG16, as the event code to ask your questions. Please be sure to indicate the person to whom you're addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end. Recognizing the limitations of a webinar with more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG16 as the event code. Today's session deals with the changing planning environment, where the changes are coming fast and furious. Looking at a future where most of our generation could be coming from resources characterized by variability and uncertainty, while we're often working with legacy tools from the days of fossil generation, this is clearly an important topic as we move into the energy transition. This session will be chaired by Ken McIntyre of MISO, who's a member of our board of directors. Ken is a familiar face at ESIG and is well known to many of you. We're very happy to have him here with us today. I imagined if I asked Ken for a little known fact about himself that I could share with you today when I introduced him, what he would tell me. And I thought that he might say that his favorite food would be meat pies and sausage rolls. I'll have to let you guess why. Ken, we appreciate your participation, and I'll now turn it over to you and give you a chance to set the record straight.
Well, thank you, Charlie. And I guess with that, I'd probably say g'day to everyone. So maybe that will help. So g'day to everyone, and wherever you may be or calling in from and joining us today. And again, welcome to ESIG's 2021 Spring Workshop Session 5. And today's topic, as Charlie said, was the changing planning environment. And yes, I am a passion to meat pies and sausage rolls. I'll confirm that. Again, Ken McIntyre, I work with MISO, and I'm very happy to be here today to chair the panel session. Firstly, we just hope that everyone is safe during these challenging times. And for that reason, I'm just really glad that we're able to continue the workshop in this fashion using the technology. But again, hopefully you're all safe, and we truly appreciate that you can take the time to join us today. Once again, ESIG staff and the volunteers have amassed a great panel, a great set of folks today to share and discuss what I believe are 3 insightful topics with you around the changing planning environment. And once again, really look forward to the questions and answers that we'll undertake at the end of the presentations. So quickly kicking this off, when I was asked to chair this, and as I think about the grid of tomorrow and how we're going to plan for that. Once again, as Charlie mentioned, facing some of these advances in technologies that is coming at us at quite a pace that we're not used to in this industry, but also the decarbonization goals that are set forth. The questions of reliability are square in the crosshairs and the focus of what we do. And then as I reflect on some of the major events and the things that we've learned over time, and then more recently, some of the things we've seen in Texas, and the unfortunate events there, there's also a question of resiliency, and that comes to the forefront of our minds as we think about how we plan our grids and where we invest. So at its core, although these questions are challenging how we may do real-time operations and maintain reliability in that time frame, without doubt, it's also a planning approach that we are challenging, and the traditional planning approaches and those traditional tools and the information, the scenarios that we analyze as we are thinking about solving some of these reliability problems. And I think the challenge is, how do we approach these things differently, and how do we think differently about solving these problems? And I think that's what today's presentations will help us think through and challenge our traditional thinking. So today's panelists will share their insights and some examples to help us start thinking differently. But as you listen and observe the presentations, I thought it might be helpful, at least for me. I captured some of the questions that I have, and maybe some of the questions you might be thinking about as you, as I said, listen and observe with these presentations as they're ongoing. And once again, use the slido.com to raise those questions, please. Some of the questions that came to my mind was, again, what information and scenarios will planners need to analyze in order to develop not only an efficient, but a reliable and resilient grid of the future? And how do we think about ensuring that operators are able to maintain reliability in the real-time time frame, given the uncertainty and the variability that we see coming? And this isn't on an hourly, this is hourly basis, right? It's not just daily and weekly planning, but on an hourly basis, there's variability that we see coming at us. And then how are we thinking about our planning approaches and what we invest in as we transition, right, and meet those decarbonization goals, and we can continue to maintain that safe production and delivery of energy to our customers. So the transition is a big component of this as well. Another area I thought about was, how does distribution or behind the meter or distribution networks play a role as we plan our future grid, and how are we thinking about that, both in the transition and then on the other side as we maintain reliability and operations? Once again, given the past events and those extreme events we just saw recently in Texas, how does grid resiliency start influencing our planning approaches and the scenarios and those investment decisions? And then lastly, I was thinking about, how do we bridge that gap between real-time operations and planning, and how do we learn from what we're seeing and the behaviors and the way that we react to conditions on the grid, and feed that back into and providing insight to our planners so that they can understand as they're thinking about designing the grid of the future. So hopefully that gets you thinking about some of the questions that you may want to ask as the presenters complete their examples today. But without further ado, I'd like to introduce the first of our three panelists today. I want to introduce Dr. Nidhi Santen. Nidhi is a senior technical leader in the Energy Systems and Climate Analysis Group at the Electric Power Research Institute, EPRI. Nidhi manages EPRI's research on electric sector environmental and policy analysis, and her technical research focuses on integrated electricity sector resource planning and the impact of environmental and technology policies on the evolution of the power system. Prior to EPRI, Nidhi worked in a wide range of organizations, including academia, consulting, electric utility, and the environmental and energy policy side. Nidhi holds a doctorate in engineering systems from MIT, a dual master's in environmental policy and atmospheric science from Indiana University, Bloomington, and a bachelor's from University of Illinois. Today, Nidhi is sharing EPRI's Integrated Resilience and Strategic Planning Framework Initiative, which gets to the core of the planning challenge of both resiliency and reliability. The topic today is linking different modeling tools and domains. So I want to welcome Nidhi and thank you for being here today.
Thank you, Ken, and good morning and good afternoon all, and many thanks to ESIG today as well for the invitation. Really glad to be here today to talk a bit about this project that EPRI is working on in this very broad but of course incredibly necessary space of integrated planning. So I'm here today also on behalf of a very large team of research staff at EPRI working on this effort at the directive of our board. As Ken mentioned, it's called the Integrated Resilience and Strategic Planning Initiative. So for the first half of the presentation today, I'm going to provide an overview of the initiative itself and some of our motivations behind it. And then for the second half, tell you a little bit more about a case study on the New York system that we've started where we're beginning to tackle one of the problems within the initiative itself. So over the course of 3 years, the project seeks to develop a modeling framework and a set of tools to analyze system integration challenges and support more integrated strategic planning studies in the industry, most notably due to deep decarbonization and other environmental goals, and the associated, of course, increased deployments of variable renewables, distributed energy resources, and the different levels of storage that may be on the system. So the effort is a joint effort between several cross-area EPRI staff from the group that I work in Energy Systems and Climate Analysis, our Grid Operations and Planning group, Distributed Energy Resources and Energy Storage groups, as well as our Customer Resources Research group, and is also being advised by a cross-area group of utility planning advisors. So just stepping back for a moment, what's motivating this? This is just an illustrative graphic associated with just one of these topics, of which there, of course, are many, many more. But here, we're asking a simple question. For example, what is the value of energy storage? Because presumably, of course, a utility, an investor, other stakeholders want to know what the value of this technology is, and ideally be able to compare it to the value of other technologies in a future power system so that we know, how best to plan for its potential deployment and use. However, as the illustration shows, there are numerous value streams for energy storage that we can analyze as we move across the dimensions shown here of, decision-making horizon and electric power subsystem. And they are really, far from independent from one another. Comprehensively understanding the actual value of energy storage in emerging power systems requires capturing the endogeneity between these values and the evolution and the dynamics of the rest of the system. And traditional, more piecemeal modeling approaches and planning approaches as well, do not span this full range of decision-making horizons and subsystem dynamics at all. And these are applicable to many key value streams in advanced energy systems. So it's determining these interconnected values, and that really requires analytical capabilities at various temporal, spatial, and subsystem levels, which currently, right now, still exist in relatively different models. So while we're, proud of the various analytical strides the research community has made, EPRI included, during the past several years, we know that, our existing analytical tool set cannot comprehensively address these questions yet. There's still, a basic lack of connectivity between individual tools and key system dynamics that, in reality feed back to the resource planning investment decision are not currently well represented. So our project is really about evolving our tool set by, developing new methods and applying emerging methods and processes, including those for data exchange between models that are needed to adequately address these questions. So looking across the same spectrum of decision-making horizon or temporal resolution that the models typically cover on the vertical axis here, and the subsystem of the power system being studied on the horizontal, You see, EPRI utilizes a combination of internal and external modeling tools, and we've already begun to work on developing some links between transmission and distribution planning in particular, as well as distribution operations and planning. But we're now beginning to work a little bit more explicitly on the red links that you see here, notably those between sort of coordinated generation and transmission planning and long-range resource planning and more detailed operations simulation. So to this, there are two additional aspects that we're highlighting under this board initiative that, if ignored, would not achieve our goals of addressing the challenges that industry is observing and the changes industry is observing and the challenges that we currently face. So the first is on incorporating extreme events into planning. I'm not going to talk much about this today, but just suffice it to say, of course, as Ken already introduced in his introductory remarks, it's an extremely important aspect of the project as recent events in Texas illustrate, and is requiring us to go beyond, figuring out how to integrate the basic aspects of generation, transmission, and distribution systems planning across long time horizons, but now really revisit how we consider elements of risk and explicitly, cost-effectively plan for robust systems that can manage uncertainties at the tails. So this is coming into the project along various dimensions, from more rigorous scenario analysis and even stochastic planning, but also even more simple aspects of revisiting how we incorporate reserve margins in our long-range planning models, or historical data for wind and solar in our future planning, and the development of potential synthetic data sets to use. So here that is a little bit pictorially. So we need to move away from these simple reserve margins and 50 percentile planning studies, or even single-year planning studies, and begin to incorporate the probabilities associated with different realizations of the future by relying more explicitly on expert climate study data, coordinated resource adequacy studies that can incorporate extreme events and consider the effects of sort of common mode failures, and be a bit more, I think, bullish when it comes to studying, what-if scenarios for tail events in the course of our normal planning analyses. And then finally, the other aspect under our initiative is to make sure that we're acknowledging the changing customer behaviors and that landscape into our planning. As we all know, of course, the end user is no longer a passive customer, and so we're working on improving our forecasting of customer behavior. And that includes elements of quantifying electrification potentials, to DER deployment, to improving our understanding about how the end user responds to prices, all to inform better planning decisions. And so again, here that is pictorially. In the past, we've simply planned to sort of meet things like peak load, or maybe ensure that supply resources on the system were controllable enough to follow demand. And we're really looking to evolve that by more actively analyzing and considering things like, DER adoption and consumer responses to changing prices or technology availability, and planning now so that, sort of the full supply curve can meet the full demand curve, and support more the decentralized matching of both supply and demand. So in sum, EPRI's effort here is really to support more holistic resource investment planning across generation, transmission, and distribution systems. And it's about working sort of at this intersection of long-term resource expansion planning with grid and network operations and planning, but with these added dimensions of considering potential climate impacts and extremes, and then changing end user participation and patterns. So next, I'd like to just turn to sharing highlights of a case study we're working on at the interface between resource expansion and grid operations and planning. Not yet, bringing in these aspects of climate extremes or end user behaviors explicitly, but taking this necessary next step towards filling in some of those links between the modeling tools we need. So the objective of our current case study is to demonstrate, really just to demonstrate enhancing long-range capacity expansion tool decisions with more granular tools. To do this, we're using more granular operation simulation tools to validate chosen resource plans that are originally developed using less granular tools, like a typical long-range capacity expansion planning model, for example. And then developing methods to update those expansion decisions when the more granular tools may show that the originally chosen portfolio was inefficient or unreliable under certain scenarios. So much of what we're also doing in this first step is just developing our own catalog of the challenges that we're encountering when using different tools together to develop a long-range resource plan. So that we can sort of add that information to the work that we know, others have already started elsewhere. It's really a growing body of literature on this topic, in different places and in different projects. So we're using some high-level framing questions to help guide us through the case study that we're working on of New York. We chose New York for this initial work both because of good data availability across the various models that we're working with, as well as the state's decarbonization plans and policies that allow for a bit of a timely investigation into this. So we're hoping that with the new tool, we'll be able to answer questions like, how much does it cost to build and operate a decarbonized electricity sector in New York? And how does that cost compare to a future without a carbon constraint? But importantly, how reliable is that decarbonized power system as planned? What aspects of reliability may be degraded most as we start reaching, really deep decarbonization levels? And then very importantly, how can the resource mix in New York be modified potentially to cost effectively respond to reliability scarcity or excesses even, while still meeting the original decarbonization goals? So for this first phase in our linking of capacity expansion planning models with more granular operations simulation tools, here's a high-level overview of the tools we're using and how they're currently being used together. We're using EPRI's U.S. region integrated generation and transmission capacity expansion planning and end-use simulation model to construct scenarios about how the electric sector, so that would be including things like aggregated capacities by technology and end-use loads, could evolve across a range of different policy, technology, and climate futures. It's not written here on the slide, but we're currently looking at futures out to 2040. So we're then bringing that information to a more granular capacity expansion planning model for MISO to develop actual unit-level generation expansion scenarios across the state. And then finally, for this initial task in the study, we're using those results in those resulting resource mixes in a detailed hourly operation simulation tool to study reliability of the implied system and then investigate and construct potential constraints that can be fed back to the capacity planning problem to ideally improve that initial CapEx decision. And then as you'll see here on the bottom right, we're going to be adding to this a step where we investigate a little bit more explicitly resource adequacy of the system, as well as utilize EPRI's Dynador tool, which helps to determine operating reserve margin requirements for us to also feed back into the higher level investment planning decision. I'm going to skip this slide, but it will be available in the slides afterwards that are posted just for the purposes of time. So I'm going to move right over to this slide. What we're focused on in the case study is really about how we can allow the capacity planning model that sees a different set of costs to make its least cost economic decisions, the relevant additional sort of more granular costs that operation simulation models see. So these are, of course, costs that are based on hourly or even sub-hourly operations across detailed nodal networks, inclusive of things like congestion and other, realistic system operations. Here we're showing two graphs from some of our early modeling runs of New York that compared these simply compare system operating costs in 2030 from the capacity expansion planning model and the operation simulation model, and just show, that the operation simulation tool with higher system costs as it considers these additional scheduling, ramping, network congestion, and other system-related costs. But then down below, from a revenue standpoint, and that's of course related to how much each of the units are being dispatched, and of course goes directly into the decision about what to invest in. It's not as simple of a story, and so here we see some units appearing more profitable, others appearing less, depending on the model that we're seeing those results through. So this idea of model granularity, and which of the features each of these models are accounting for, ultimately affects the decision about capital investment, and that's really one of the main motivating factors for the work that we're doing. These are some snapshots again showing total dispatch between different technologies being quite different when looking through the different modeling lenses of the capacity expansion versus the operation simulation tool for the same system and with the same resource mix on the ground. So what we're working on is integrating these models, integrating these sort of more detailed hourly and sub-hourly dispatch snapshots that can highlight periods of system stress and scarcity across a range of different build-out scenarios into the capacity planning to make it more robust against these changes that we'll be seeing in the system with things like higher renewables and distributed energy resources. So this is how we're doing that. Here, this is just a pictorial overview of the integration method that we're using. The basic method consists of two main sort of points of analysis between the CapEx model and the more granular operation simulation tool, in this case a production cost model, and then four different interfaces where data and information exchange needs to happen. Between the CapEx planning tool and then the detailed operation simulation tool, we have a data analysis step that determines representative and extreme periods to estimate expected operation costs and choose the set of resources that does ensure system reliability and flexibility. And then we're performing a separate analysis using the detailed operation simulation tool on representative and extreme days to reveal scarcity on the system or potential excess. And then once we have that information, we estimate incremental collective flexibility requirements to be enforced in the long-range capacity expansion tool as that feedback. So the point here is that the more granular operation simulation or production cost modeling tool can really help us make sense of what we may expect from the capacity expansion tool's decisions. May it be this, resource scarcity, or maybe there's an excess of capacity. And the goal is to feed that information that we can learn from the operations model back up to the capacity expansion problem. Of course, the problem is that, we can't use the detailed granular model to explore these more realistic operations over the full time horizon of the CapEx model, right? The problem just gets too big, and if you could, we wouldn't have too much of a model integration problem, probably. So we need to be somewhat smart about looking in detail at expected operations across a set of representative days and also extreme days. So just making sure to look across these extreme days will allow us to make sure the system will have sufficient resources to respond to things like high ramp days, high peak days, et cetera. For example, of course, days when there's a lot of renewable generation, but also when dispatchable resources may be at their floors. So here's an illustration of some of the work our team is doing under the hood on finding representative days and extreme days for further analysis in the detailed operations tool. So this describes that first step of finding representative and extreme days. So we're looking at yearly data of load, wind, and solar, and creating clusters of net demand. And from those clusters, we're looking for representative days, which can often, be a first good proxy for operational costs. But then on the right, the little boxes, this is an illustration of what we're doing to look for extreme days. Here we're looking to maximize particular features of the system, asking questions like, which are the days with the steepest up ramp or the down ramp, max peak, minimum valleys, maximum energy, et cetera. And we can choose really any particular feature that we're after, sort of identify that day, and then run the operations model on those particular days over a wide range of uncertainties and realizations of future conditions to see how the system is equipped to respond to different stresses, to see if it really possesses the flexibility required to respond. The second stage is then focused on analyzing the results from the operation simulation runs over the various scenarios. In the detailed operations model, we're now able to perform scheduling for the day-ahead market, but then also use some of the multi-cycling features of these more detailed models to assess what happens when uncertain system conditions are then varied in real time. So this is, again, an illustrative graphic, but what we see here is the black line, in the black line, the day-ahead schedule. In the blue line, what the system is actually able to produce in that hour. And then in the red areas, we see periods of load balance violations where the system maybe doesn't have enough, ramping capability or reserves, for example. And so what we're doing is analyzing these violations further, sort of studying their magnitudes, durations, rates of change across many different characteristics of the violations to then help us develop this set of collective flexibility constraints that we send back to the capacity expansion problem to sort of help it make a better decision in the next go around. And then finally, this is my last slide. This is just a quick note on the several steps we have next in the New York case study that we're currently working on. After we feel sort of sufficiently comfortable in being able to improve the capacity expansion planning step to consider these additional costs and reliability requirements that these more detailed models see, we have sort of this laundry list that will help us address some of the other challenges and needs that I mentioned up front in the presentation. So to adequately sort of merge this improvement with the needs of integrated GT&D system planning, we'll be extending the case study to consider various aspects of sort of new generator siting and transmission build-out scenarios, the impact of distributed energy resource deployments on end-use loads and distribution system needs. And then last but not least, we also have a team looking at developing a fuller set of renewable profiles and other system situations that can help represent probabilistically future climate scenarios and potential extreme events. So Ken, that's all I have for today. I know that was a bit of a whirlwind on the EPRI project, but I hope it gives everyone at least a high-level look at a little bit of what we're working on and one of the main projects we have going on in this space right now. And thanks again for having me.
Well, thank you, Nidhi, and no, that was fantastic and really sets the scene around the challenges around a modeling framework and the integration of the information and data, as you touched on, those real-time operating representative days and extreme days. So I think that was touching exactly on some of the opening remarks. So thank you for that. Keep those questions coming in Slido as well. So appreciate, we've got a few on there already. So keep those coming through as we work through these presentations. Without further ado, I'll get our next panelist introduced, which is Dr. Charles Philbrick, which he would prefer to be called Russ. So Russ is a co-founder of Polaris Systems Optimization, which manages the variability and uncertainty of renewable energy with optimization-based decision support tools. Very important stuff there. He has developed many of the market clearing engines currently deployed in power markets and vertically integrated utilities, including the first commercial deployment of mixed integer programming security constrained unit commitment by the PJM interconnection in 2004. So very impressive, Russ. He's also got 28-year veteran of the U.S. Navy as a submarine officer, and has also has several thousand hours experience in direct supervision of nuclear plant operations. Today, Russ is sharing insights into the impacts and relationships of real-time operations and those operational behaviors that we just heard from Nidhi during events such as extreme events, but understanding how this could better inform our planning process. So again, challenging our traditional planning approach. So first of all, welcome, Russ, and again, thank you for your service. And thank you for presenting today.
Thank you, Ken. You did your research. Yeah, I really appreciate the comments before. As Nidhi described, we face difficulties in integrating results across the wide range of planning tools that we face. And in this talk, I'm going to shift a little bit to discussing problems that more or less affect all the planning tools, and particularly a few of the concepts behind variability and uncertainty. And then listening to the introductions by Charlie and Ken, I was reminded of my own journey in trying to understand what's different, because the impact of renewables is challenging us in ways that we're not familiar with, and it's not obvious what needs to change. And so I hope in this discussion I'll be able to present a little bit of that. I began seeing this 15 years ago when I was asked to attend what was in UWIG instead of ESIG, Utility Variable Integrate. Actually UWIG, Utility Wind Integration Group, telling the audience what we were doing at Alstom back then to support integration of wind, and we had no idea. It was trying to fit the square peg that we've had in the past into something that was different. And I over some time, I figured a few things out with the opportunities to be part of the ESIG community and the great group of folks that comes together to try to understand these things. And in this presentation, I hope to share with you some of the understanding that I got from the discussions with this great group, and how variability and uncertainty affects the planning process in ways that are different, and how many of the assumptions that we've used in the past have to change. And I hope in the end of this, maybe to help you think a little bit differently about how to approach some of the planning problems and where to question the use of the tools that you have today. So to start this off, I want to talk about the tails of the distribution, because really this is driven by the variability and uncertainty of wind and solar. And we all know that the tails of a distribution are generally the causes of the most costly extreme events, both in terms of economics and reliability. But also it's important to understand that the degree to which these tail events affects economics and reliability depends upon operations. How we've set up the control room to be able to manage these tail events will have a major impact on the actual performance of the system. And then if you take that into a planning process, you need to understand how those operations will handle these tail events in order to know what the value is of all the new changes that we're making to the system, be them new resources or be them changing practices and policies in the control room or regulatory environments or wherever. And the tools need to capture those operational processes to capture correctly the outcomes, because if we don't, the answers in planning are wrong. And so we need to recognize where the tools we've had in the past, they can still be used effectively, but where we need to start questioning the validity of the results that we get out of that. And I'll bring up a few examples to help illustrate that. Okay, to start with, let's talk about what the tails are. And just because it's topical, I've taken prices from the public prices from the ERCOT website for February for the last 12 years, basically the years that are available on their website. And we've just been through a difficult time in their grid, but this is not the first time that some of these issues have hit. Back in 2011, there was other cold weather event that caused losses of generation and high price spikes. And the plot that you see here is showing the distribution of 15-minute prices for ERCOT in real time for the month of February in 2011. And below is the distribution of those prices. And this is when we talk about the tails, we're talking about the extreme prices that we see. In other words, the high and low tails of this distribution. And this February, you can see that there were a fair number of prices between $100 per megawatt hour and the price cap. I showed this is $10,000 per megawatt hour because there are some prices that are slightly over $9,000, which is the ERCOT price cap. So when we're talking about the tails, we're talking about these kinds of extreme events. But in general, it doesn't have to be this extreme. Even the tails in more modest ways still matter from an operational standpoint. And this ties into a slide that Nick Schlag from E3 presented at the ESIG meeting 5 years ago today. Well, actually a month off, 5 years ago, he presented this slide, which I thought was a great illustration of some of the challenges that we're facing with planning. In application of the production cost modeling tools that they're using, and I would say that this is true of all tools when used in a traditional manner, you get simulated LMP prices that follow the blue line in this plot. But when you compare that to the observed prices, you see that you're missing the tails. And also, interestingly, that the median prices that you see are lower in reality than what you simulate. And there's good reasons for these differences, and I'll talk about that. But the point here is that if we don't capture these tails, we're not actually capturing reality. So going back to the ERCOT example, these are the February real-time prices plotted from 2011 to 2021. So you can see the 2011 prices that I showed earlier and the peak prices that occurred. And you can see the 2021, which was by comparison a major departure. That the amount of revenue or the amount of cost reflected by this departure is massive, and we're seeing huge financial consequences from that for many of the participants in the ERCOT market. But to take a little bit closer look, I've expanded that previous plot to just show from $0 to $100 because I want to make a few points. Again, reinforcing what we've discussed already. And I've picked out a few of the years, 2016 as a kind of typical year, but it's actually the lowest of the years in the plot. 2011, 2014, and 2021. So in 2014, there were some events also, but in that case, it didn't have quite the tails that 2011 and 2021 did. If we compare the real-time prices to the day-ahead prices, we see a very similar picture. But there's a very important difference here, and if I'm going to overlay these two on top of each other, so you can compare the real-time prices with the day-ahead prices. And just as in Nick's slide earlier, we see that the median prices in day-ahead are higher consistently, but the extreme prices in real-time are higher. So the question is, why is this happening? Here are the real-time extreme prices, and we can see that the real-time extreme prices indicated by the red diamonds here, sorry, I should have changed the legend, are many times higher than the high day-ahead prices shown by the green dots. And you say, well, what is different about these two that allows for the prices to be different, but the median prices in day-ahead to be higher? And the reason is virtual trading. Virtual traders are very good at risk management, and they are recognizing there's an opportunity to make money by buying power in day ahead to sell back in real time when on the hopes that they hit it right and get some of these extreme prices. Most of the time they don't, but sometimes they do, and when they do, they win big. And to see that effect, we can look again at the prices for February and this most recent event. If you look at the day ahead and real time prices, roughly the revenue under both day ahead and real time is about the same, showing that the traders have been very effective in capturing that that revenue stream from the divergence. And all the markets depend on this. Day ahead and real time markets are not the same. The differences in a well-designed market are still significant enough that you need virtual trading to help maintain consistency between the markets. But that's not to say that they are the same. The distribution of events that we see in real time is much more extreme than what we have in day ahead. And if we're trying to plan for how the system is actually going to be performed, we need to model those extreme events. This is just the same plot, just stretched out. Instead of showing 0 to 100%, it's showing 0 to 30% of non-exceedance. Again, just showing that the distribution of prices on average is the same. So now we've discussed the tails. The question is, who's responsible for managing them? You know, the Texas example recently is a tragedy, and to some degree, it was unavoidable. You know, extreme events will happen, and we will always be faced with events that are out of what the market can handle. But in other ways, we may have made it worse because of not having the appropriate level of insurance to prepare for this. And so someone has to manage that. Someone has to say, how much insurance do we purchase to protect ourselves against this? Because it costs something. And if we leave it to the markets in a very competitive market, sometimes it doesn't get done because you can't compete. So who manages the tails? The first thing I'd say is everyone does in the end, because we all contribute to it. The tails are a result of the collective impacts of everyone, all the loads, all the generators, the regulators, the market operators, the planners, and we all need to work together to solve that. But that doesn't mean that we all have an equal responsibility to manage the risk associated with that, because it's difficult. You know, traders are very good at it. Homeowners, not so good. They don't have the data, the resources, the time to focus on it. And based upon the events in ERCOT, you could argue that there are many other parties that probably don't either. There are quite a few of the load serving entities that are going to be going out of business, it appears, because they were not able to manage that risk themselves. So we have to recognize that there are different roles in managing risk, and where people need insurance, we need to provide that insurance. So just going back to a point I made earlier, managing the tails begins with planning, because the outcomes that we see in markets or in vertically integrated utilities depend upon the operation practices that we see in the control room. The operations that are conducted, how they're conducted, and what's available for backup resources depends on planning. But planning depends on accurately simulating the future outcomes that we get from different choices that we make. How do you know what different resources are worth and the value of their flexibility if you don't capture their ability to deploy that flexibility in meeting the operational needs? And this challenge affects all different planning tools to greater and lesser degree. And we could have a long discussion about each of these. And I'm not going to get into any of these in any depth, but just to point out that in each of these tools, we've made simplifying assumptions that traditionally were not bad and made our lives a lot easier in coming up with answers to the important questions for investment and operations. But with the increasing integration of wind and solar, we need to go back and question those assumptions and recognize that some of those assumptions are no longer valid. And it's not valid, and as is obvious, the mix of resources in the system is changing dramatically. It's a slide from Kathleen Spies at the Brattle Group showing what over the last 10 or so years has retired and what has been built, and how different that mix is. And you can just, from other discussions, understand how it affects the operational practice of the system. So the important point about this is that with these changes, if we do not do better with understanding how they play out operationally, how the decisions we make in a planning context affect the actual outcomes that we see, we're not going to be making very efficient decisions from a planning perspective. And what I'm showing here is the result of a recent study by colleagues. This is from the Boston University Institute of Sustainable Energy. Colleagues connected mostly through the Brattle Group. Kai Van Horn is now with National Grid, and Pablo Ruiz is also with New Grid. In looking at the value of new transmission facilities by looking at what we could call a single cycle view of the future, where you just simulate the future as a traditional kind of day ahead process, as we typically do, hourly decision making for 10 years or 20 years into the future. They see one set of prices. When they look at what happens when they include a more accurate operational simulation that addresses both day ahead decisions and real-time decisions, they see cost impacts of new transmission that result in 2 to 20 times more value to the new transmission facilities. 2 to 20 times is a pretty significant difference if you're trying to decide where to go with new investments in the system. And it's an example of one of the aspects of transmission planning and all planning that is necessary for managing with higher renewables. So going back to Nick's slide, we can understand that a big part of the problem that he was addressing is due to missing simulation of operational processes in how we do our production cost modeling and other planning efforts. And a lot of that's due to the impacts of uncertainty and variability on operations. And just to give an example of that, by doing an operational simulation and comparing might call a single cycle day ahead process against a 2-cycle day ahead plus real-time process, the right-hand plot is showing a result that is based upon real-world data for a utility that I'm not allowed to mention, but provided by EPRI and TCR, where they actually had day-ahead and real-time data that they could run through an operational simulation process. And you can see that by looking at just the single cycle decisions and comparing that with the 2-cycle decisions, you get the tails. You start seeing the tails that are missing from the traditional planning process. The reason that you don't see this very often is not just an issue of tools, though. It's also an issue of data. Having data to do something like this is very difficult right now. There are very few data sets, even within the utilities, that would allow you to do a kind of multi-cycle operational simulation. But this is going to be increasingly important in order to capture the impacts of renewables on the system and how we need to respond to those, and what the resources and changes are that are most appropriate to addressing those needs. So here's the big point from my presentation here is that the planning problem, you could say, does not include operations, at least not to the degree that it needs to with the way the grid is changing. The assumptions that we made in the past were effective and reasonable given the nature of the system we had 20, 40 years ago. But increasingly, the processes that we see in the control rooms has evolved, and it's evolved in a way that planning has not kept up with. There's many different decision processes in the control room: long-term planning for those for maintenance outages, scheduling of inflexible resources, day ahead, real time, intraday reliability processes. And at each of these points, there are different, we can call recourse and non-recourse decisions that have to be made, and how we make those decisions is critical. The longer you can delay a flexible resource, making final decisions about a flexible resource, the more flexibility you can extract out of that to respond to the tail events. Traditional planning processes also have left out other details that are important. As Nidhi identified, some of these details matter: zonal versus nodal modeling, and metrics, peak capacity versus what happens during the fall and summer when we start seeing reliability events. And in summary of this, I'd say that one of the important things is that multi-cycle modeling is an important tool for managing this, that you need to start recognizing that the decision processes in the control room are characterized by different decision cycles, and that that's going to be a key to being able to model the impacts in planning tools. To leave you with the final, just one more comment. There are many questions that we have to answer, and many of these questions we can't answer accurately without having the ability to simulate operations more accurately than we have. How do we know what the value of an improved forecast is unless we know how that forecast is going to be used operationally? So to leave you with one last slide, and again, another slide from Kathleen Spies, we need to think differently. The way we've dealt with needs of the system in the past worked in the past, but things have changed. And if we don't think about them, about how those changes affect the way we need to plan for the systems of the future, we're not going to get the right answers. So with that, thank you, Ken.
Thank you, Russ. Very good. Appreciate it. Keep those questions coming in on the slido.com. So appreciate people starting to do that. Make sure that if you see a question there you like, please add a like to it, and that'll get it prioritized for us to get ready for the Q&A. Once again, thank you, Russ. Very helpful. I'll move on to a third panelist in the essence of time, and final presentation today with Greg Huynh. Greg manages the Los Angeles Department of Water and Power's 100% Clean Energy Innovation Group that is currently engaged in several initiatives to bring clean power into the Western energy grid. Greg leads the team that is spearheading efforts to conduct a comprehensive study of how the city of Los Angeles can get to 100% renewable energy. So very topical. Greg has been with LADWP for over 10 years and has worked in various parts of the department, ranging from project management, power plant operations, and power planning. Today, Greg is presenting on a goal that is becoming more and more common, that impacts all of us as we think about our pathways forward in modeling and integrating and looking at the benefits and costs and trade-offs towards 100% renewable energy. Greg's topic is the Los Angeles 100% Renewable Energy Study, also known as the LA100. So welcome, and thank you, Greg.
Thank you, Ken, and thank you for the opportunity to be able to present today. I will apologize to everyone today. I am a bit of an underachiever compared to my panelists. I do not have a PhD or a doctorate in this field, but I will do the best to not make a fool out of myself this afternoon. Thank you again for letting me be part of this. As Ken mentioned, this is the Los Angeles study that we had been engaged in with the National Renewable Energy Laboratory, NREL, to help us understand what it would take for Los Angeles to get to 100% renewables. And this is a good opportunity for me to present to you where we're at with the what we're calling the LA100 study. As a bit of background, back in 2016, our city council in Los Angeles approved a motion to direct the LA Department of Water and Power to evaluate what the pathways were and what investments that we had to make to get to 100% renewable energy, while at the same time remaining a high degree of reliability. Those two pieces are extremely important for us, not only the reliability of the system, but also providing clean energy. The difference between this study and what you'll see out in the industry is that this study, what part of the mandate from the city council was to engage with one of the national laboratories, which is what we did with the National Renewable Energies Laboratory, NREL, to do a comprehensive bottom-up study to understand the investment pathways, but also what were the potential benefits of the environment and to health, and to monetize those into costs, to look at, because Los Angeles is such a diverse community, what would the effects be on what we call the environmental justice communities, communities that have been typically underrepresented in these types of studies, and then also looking at the job and economic impacts that something like this, us getting to 100% renewable energy, what that might do to the economy and local jobs. So not just a technical study, but a comprehensive study that is really informing us and how our community will look once we get to the future. So what makes this different than what we would typically see from a study? One, it's being driven by the National Renewable Energies Laboratory. It's the first of its kind in that it's looking at 100% renewable energy on such a large system like LA's. We have 4 million customers out here in a system that spans not only in the LA area, but spans up north to the as far north as Washington and to the east, northeast in Utah. And so what makes this difficult is, one, we are a large system, and how do we balance? We are also a balancing authority for other cities in the area, Burbank and Glendale, and how do we maintain that energy supply at all times? Looking at the complex integration of the different models, we are a vertically integrated utility. We generate, transmit, and distribute, and so looking at that in its entirety, from generation all the way down to the customers, and in the integration of each of these different pieces makes it incredibly complex. And so the detail that we are looking at when NREL had run the study and the modeling, we're talking about millions and millions of simulations. The information that we're getting, like I said earlier, from a bottom-up standpoint, looking at over 700,000 agents from the customer side to really understand how our system works and model it in a way that is comprehensive. Where the study does stop short, though, is that this study itself will not make any recommendations because it is part of the national laboratories. They will not make any recommendations or suggest any policies. So that's when this is all completed, it'll be put back in the hands of our engineers and our planners to go back into our integrated resource planning mode to see what the future is going to look like based on the information that we gleaned from this study. So the different components here we can see on the screen here is broken down into 3 pieces: the customer, the power system itself, and the community. And so, like I said before, this is different in that we are trying to hit each one of these pieces and do it in a very comprehensive manner. That it's not just looking at the technical pieces of the power system, but looking at doing projections on what the customer and their customer behaviors when it comes to their demand, EV adoption, rooftop solar adoption, and then looking at the community as a whole, what the benefits and the challenges are with reducing greenhouse gases, air quality, environmental justice, and jobs. So also discussing what the community involvement was. We didn't want to do this in a bubble. We didn't want to do this just as an academic study. We really wanted to reach out to the community and get a breadth of representation so that we can help, so that they can help inform how it is and guide the study in a certain direction. So we had formed this advisory group that provides input and will periodically review throughout the study. We would have, for the last few years, had quarterly meetings with this advisory group with representatives, having representatives from environmental groups, neighborhood councils, academia from the local universities at USC, Northridge, looking at getting input from our premier accounts, which would be our very large customers like LAX, the LA Unified School District, different business groups and other utilities like SoCal Gas, being part of this wide spectrum of people to help look through our study and inform what it is that it would be important to them and how to integrate that into our results. So this slide that I show here on the screen here is really the crux of our study. It's scenario based and looking at the different pieces and the different sensitivities if you hold one thing constant, and what would it do to the effects of the other pieces. And so I'm going to take a little bit of time to explain what's on the screen here. So looking more on the right side of the screen, we have three pieces here: the moderate, high, and stress. These are different demand projections and different levels of electrification that we're seeing on the system. So the moderate is if we kept chugging along as we are now in terms of the different energy efficiencies, electrification, and demand response programs that we're doing right now. The high is, of course, the high piece. If we were really to accelerate what that looked like, if we were to accelerate high electrification and these different demand response programs, what it would do to the to each of the scenarios. And then we also have a stress case, which is kind of a standalone case in that if we were to go with the high electrification, but we're lagging in some of the like energy efficiency programs that we were looking at, and what it would do to the system and how it would stress out the system. And so looking at those different levels of electrification and now looking at these four scenarios, which I will go over in a bit, we had a total of 9 scenarios, 4 for moderate, 4 for high, and then one stress scenario. So looking at the different scenarios and their different characteristics, we have what we call SB 100, which lines up with the name of the California Senate bill that requires us to get to 2045 and 100% clean energy. In this scenario, we looked at all 3 of the electrification targets: moderate, high, and stress. This target, this scenario, takes us to 100% clean energy by 2045. This differs from the other scenarios in that it looks at retail sales and not generation. And this is the only scenario that allows gas, allows up to 10% gas with an offset of renewable energy credits, and allows for nuclear and upgrades to the transmission system. So here's what you would consider what the legislative requirement is going to be, and one end of the spectrum. This allows for the most flexibility out of all the other scenarios. Looking on the other end of the spectrum, we have this early and no biofuels, and it's just like the name says, instead of getting to the target of 2045, we get to our 100% clean energy target by 2035, which is 10 years sooner than what the legislation is requiring. And not only does it accelerate our target, but it also doesn't allow for different types of fuels like natural gas and biofuels. So it restricts those pieces. And so makes the target a much harder to hit, but it is something that we looked at in order to get a complete picture. And in between those two pieces, we looked at 2 different other scenarios. One, what we call limited new transmission, both for the moderate and high load electrification. This target has clean energy by 2045, but the difference between this is that it restricts building more transmission outside of the basin, and really only allows the upgrades that we are currently planning. So what this is really looking at is more so what can we do in basin in terms of demand response, distributed energy resources. Converse to that is if we were allowed to build new corridors, we have this transmission focus, which also has a target of 2045, but allows for us to build new transmission corridors to alleviate the in-basin needs. We can go out to get solar from New Mexico or the different different areas in our region to meet our 100% clean energy goals. So again, this is where everything is based. The study is based on these 4 scenarios. When it comes to all those different pieces that I had mentioned, it breaks down each one based on these 9 scenarios. So when we look at the results, this is a very high level overview of what the results are telling us, and what big picture, 100% renewable energy is achievable. But really what it would take is a broader set of resources to help us get to those goals so we can lower those costs. We believe that with wind and solar resources and those renewable energies, we can meet our needs to 70 to 90%. That last 10% is going to be a challenge in that we still would need dispatchable resources. And so that's this third bullet here, talking about potentially in-basin or out-of-basin renewable energy-fueled power plants like hydrogen that will allow us to maintain reliability and provide that dispatchable energy. In addition to that, storage is going to be critical because we do have to balance out the overbuild of solar and wind resources with the effects on our customers and their rates. And so looking at the visual here on the right side, you'll see here this first column is what we have today. Looking at the four scenarios on a high electrification basis, you'll see that there is a massive build for wind, solar, storage, and so these four scenarios have that all in common, in that there's a very large I wouldn't call it an overbuild, but a large build for these solar these renewable resources as you get to 2045. So the commonalities between all 9 scenarios are what we show here. There is going to be a need for electrification, efficiency, and flexible loads. So these are your demand response programs. These are your energy efficiency programs. We're going to need much more of that as we move towards the future. In this middle section here, the customer rooftop solar, renewable energies, and storage, as I mentioned earlier, we're going to need that as well. And then upgrades to the transmission and distribution systems. And then looking at this last part, the renewably fueled combustion turbines are really what's going to take us to that last 10%, as I had mentioned. And so this is a paradigm shift for us, in that where this was reversed. It was that we would rely on the combustion turbines most of the time, use those daily. And now we have a shift here looking at either biofuel or hydrogen, where we would use that less frequently. So you'll see here, as we talk about the different planning shifts, this is a huge shift for us, in that we typically would use our combustion turbines as base load or as peakers, but now we're really using them more as peakers, whereas this renewable energies are more of our base and the crux of our resource stack. So looking at costs, this is a question that comes up a lot. How much is this all going to cost? And looking at here, the numbers themselves are important, but they're more so this really is to show what the different cost comparisons relative to each other and what those differences are. And so one thing to keep in mind as you look at this is the cost for the bulk energy system. And it's dominated by the investments that we need in wind and solar and storage. This does not take into account the distribution system. And so looking at this, relative to each other, SB 100 would be, because it has so much flexibility built into it, would be the lowest cost. And then on the other end of it, when you look at the early and no biofuels, because again, it has the least amount of flexibility and accelerates the goal of 100%, we have a much higher cost relative to the rest of them. So looking at now what the combined effect is on our greenhouse gas emissions for the utility. I apologize, this may be a little bit hard to see in your screens because the colors are quite similar. But looking at SB 100, and as we get to from 2020, where we are now, that first bar, 2025, we have a huge reduction of greenhouse gases, because we are going to be retiring one of our last coal facilities called the Intermountain Power Project in 2025. So even just with that, you'll see a huge reduction in the greenhouse gas emissions coming from the utility. Then looking forward, of course, once the coal unit is taken offline, you'll see a continued reduction as you move through time. And then even looking at the other scenarios, early no biofuel, of course, is going to reduce it much more quickly than the other scenarios, the transmission focus and the limited transmission. So this, you'll see here, is a significant reduction moving from today to 20 in each 5 years to the ultimate goal of 2045, where there are no more greenhouse gas emissions coming from the utility. And then looking at looking at it as a whole, looking at our contribution from the power sector, relating it to or relative to the building sector and the vehicle sector. You know, our contribution even today is not quite as high as it is compared to vehicles. But even moving through the future, you know, our contribution would be much less, and much less as we get towards the future and to get to 2045. So again, the other components of the LA 100, looking at air quality, health impacts, the monetization of the benefits for health and greenhouse gases, the environmental justice analysis that we're doing, the net economic effects, and the workforce needs. You know, this really rounds out the study in that, again, it's not just a technical study, it's more of a community study, looking at the transformation of the power system and how it'll start to affect these other pieces for our communities. In terms of timeline, you know, we're getting towards the end of the 100% renewable energy study. We're out of the final stages. We have NREL has completed most of the study. It's now just going through a review. We do plan on coming up with some big news in the next couple of weeks as we get this the study finalized. So keep an eye out for some big news coming out of LA in a few weeks when it comes to this study. So we're really excited to be able to showcase this and show what it is that NREL has been able to do for us in terms of its modeling and just the comprehensive look at our system and the effects of what it can do for our future. So when that release comes out, you'll see that there's also going to be a website, an interactive website that you can start playing around with the different modeling features. It's going to be very interactive. You can start playing around with the different electrifications and seeing how it affects the system. And so we're really excited to release this. Right now, currently, it's unavailable. But what we do have, we do have 2 videos if you want to get more information about what we're looking at. We have 2 videos on YouTube. I'm sure once this is shared, you'll be able to click on those links and see what our study is all about. And with that, I'll turn it back to you, Ken. Thank you all for the opportunity again to be part of this panel, and so I'm looking forward to your questions.
All right, perfect. Thank you, Greg. So got a few questions coming through. So Greg, just take a drink of water there, because I'm going to hit up some other folks first. There's a couple questions here, and Russ, I think this is pointed towards your presentation. There's a number of questions around if you could explain what you meant about multi-cycle study approach versus single cycle. So if you could probably spend a little time on that.
Sure. Sorry I didn't take more time to explain that. But I would start by asking you to think about what happens in the control room. Each day there are maybe unit commitment decisions being made for tomorrow. Each 5 minutes or whatever periodicity, you're sending out real-time dispatch decisions. Every day probably you're also making decisions about dispatch of your inflexible coal plants and pump storage hydro and so forth. Each of those decision processes you can describe as a rolling horizon model, where you make a decision now. Some of the decisions you make are final decisions. Other decisions are provisional decisions. You can change those decisions based upon new information because you have flexibility to update your policies later. You know, if you have a quick start CT, you don't need to make commitment decisions for those day ahead. You can make them much closer to real time. And so each of these decisions processes is a rolling horizon kind of modeling approach. And in natural form, that's how you'd like to simulate them also. That one rolling horizon process is a decision cycle. When you combine day ahead with real time, you now have 2 decision cycles where you've got a day ahead decision process, and interwoven into that is the real time process. And there are feedbacks between each of those. You've got day-ahead commitment decisions feeding down to real-time dispatch decisions. You've got observed outcomes in real time, forced outages, for example, feeding back then into the day-ahead decision process based upon how the control room is set up. If you have a forced outage in the system, you have some things that can respond immediately. That's why we have contingency response. But other things might take longer. It might take you until the next day to begin starting up that next big power plant that needs 12 hours to get started. So this integration between the decision processes is important. And that's why I describe it as a multi-cycle process, because you can't just do each separately and then combine the results. You have to see those feedbacks between day ahead and real time, and from real time to day ahead, and all the other processes that are there also. And I'm talking about this mostly in the context of production cost modeling, but it applies to all decisions, even if we're dealing with capacity expansion or resource adequacy or maintenance scheduling. They're all, in a sense, the real process is a multi-cycle process. And all I'm saying is that we need to reflect that in our simulation.
Thank you. And I would imagine storage is part of that complexity too. So how we think about
Certainly
modeling that. So just thought I'd just add that as well. Thank you, Russ. Next question, I'm going to kind of combine two, because I think Nidhi would be perfect for this. There's a question around, given the high level of complexity involved in the modeling, which we've talked about. Question is, what kind of steps, or how do we think about ensuring that various stakeholders and decision makers accept the results, right? So given the complexity and trying to communicate that, I think that also goes along with maybe, Nidhi, if you want to touch on that, as well as your consideration of the tools, and are they going to be proprietary tools or open source tools, and maybe folks that are helping with those tools to get buy-in and understand the results to further along that people accepting the results. So I'll combine those two. Nidhi, if you want to have a think about that question.
Sure, Ken. Thanks, and thanks for the questions. Yeah, I think I definitely saw that theme in the question thread here, and it's such a good question. And I'll tell you, first off, the question that we probably get the most as we are presenting our work on this integration initiative and the modeling that we're doing. I think it just, I think we should I'll take it back to the team that we really need to have a slide up front describing this exact question. So I'll take a stab at it in that, okay, so in terms of this idea of, what steps are needed to ensure that the results are accepted, and also I think that goes with the next question of how do you sort of deal with deregulated markets versus regulated markets, where the decision makers are different and the investors, the investment decision makers are different, right? So first and foremost, the work that we're doing initially definitely is to support that higher level. I hate to use the word hypothetical, because that's never well received, that we know why are we doing what we're doing, but sort of central planner to understand what the needs of the system actually are. Because Russ touched on this in his presentation. It's those needs that drive that drive the costs and opportunities that different investors are going to see. And so sort of first and foremost, we have to understand what the needs of the system actually are. Once we get there, of course, there's going to be a range of different tools that we can then use to allow understanding that system need and the opportunities that need creates from different perspectives of possibly an independent power producer, or somebody, a utility that operates within a deregulated market, where there's possibly a capacity market that they need to consider investing in for, versus at vertically integrated utilities. So I guess I just want to, high level, we're first addressing system need. And then going to address questions about sort of understanding it from different perspectives. On the accepting of results. So I think I mentioned this very, very quickly. We do have an advisory group there's an executive level advisory group of utilities that operate across different markets. And in vertically integrated situations, as well as not even utilities themselves, so other sort of external industry stakeholders advising this entire initiative. And this is definitely a question on their minds. So that's one way that we're wanting to make sure that the work that we're doing is touching on actual industry needs. We're also, as the work develops, going to be making sure to be presenting it in different forums. This ESIG presentation's a perfect example of that, but also throughout the peer literature and other conferences. And then on the open source piece versus proprietary, EPRI is sort of fiercely, software agnostic. Of course, we use different tools to do our analyses. But we are planning to make the results of our work public and do a bit of integration and work directly with software developers to sort of make sure that the learnings can be integrated across the board. So hopefully that provides a high-level answer to all of those. And I'm happy to follow up with anybody in particular with more detail.
Yeah, no, that's great. Thank you, Nidhi. And I think my 2 cents worth, obviously, as we educate ourselves in the industry on the criteria and the data that we're using to make decisions, obviously a transparent, I use the term, the appropriate level of transparency is always needed so people can understand and bring them along. So I think that goes hand in hand with dealing with that and bringing people understanding the results. There's some questions here around how do people get access to the data that's needed to simulate operations. And I think I might broaden that to kind of data challenges as you think about what have you experienced? So maybe who would like to jump in? I'm going to open that up to maybe your experiences and what data was available and how accessible it was, and then getting that operations into planning.
Well, I will speak on behalf of some of the folks that I work with. One of the challenges is that there's not a lot of real-time data available, even within the organization that may be supported. Greg could speak to this. You don't necessarily even archive the data that you want to do some of the operational simulation. What we have out there is what has been required in the past. The FERC requirements for data, the public data sources that people use are of one sort, of the sort that we would have used traditionally in production cost modeling. And there's really no standards or requirements to share more than that. And because the practices haven't been developed, there's not even the practices within the organizations that have their own data to save the data in a form that can be used.
Okay. Let me do the last question before we wrap it up, because I want to be respectful of folks' time. Greg, there was a couple questions here. One was around the question around why have a was it non-bio scenario? So maybe just touching on that before we wrap things up.
Sure. Yeah, the no biofuels scenario was really put in there to understand, if we were to really go deep with this idea of decarbonization. It was something that we used to understand, like I was saying, if we were to have a lot of flexibility versus not much flexibility at all. And so how to do that would be to restrict one of our potential fuels and see what the effect would be on price. And so what I do want to emphasize before we do leave the scenarios that were presented, we're not going to pick one of them to move on with our planning. What that was is really just to look at what the effect would be on the system. Once this is all completed and the study is finalized, we're going to take the information from each of those scenarios and then plan the system. It's not that we're going to choose no biofuels plus high electrification. It's not anything like that. It's taking the data sets and taking the modeling back into our own planning process and do what makes the most sense. And so that's the way we should really look at it. That no biofuels scenario is really just on. I don't want to call it extreme, but it's just more on the restrictive end and what it is that was possible for our system.
That's a great clarification. I appreciate that. Well, I think it's time to wrap things up. First of all, I'd like to thank our panelists, Nidhi, Russ, and Greg. Thank you so much for your presentations and for answering some of the questions today. Once again, I think the session has offered some great insights into this changing planning environment. So appreciate those insights. And I hope that it's provided folks that attended today some food for thought. And as you think about challenging the traditional planning processes and tools that we use. Charlie and Ryan are going to collect the unanswered questions, and we'll get responses from the presenters, and they'll be posted. So thank you for using Slido website and putting those questions out there. We appreciate that. Again, I'd like to thank the ESIG team for organizing and supporting this workshop and continuing our ESIG mission and during this pandemic. So I really appreciate the effort to keep this going. However, I do look forward to the day where we can be face-to-face again. So I will just say that. With that, I'd like to just remind you a couple things. The spring workshop sessions will be held on Tuesday and Thursday through April 8th. We have a session this Thursday on the, as Charlie would say, the wonderful world of green hydrogen, chaired by Bethany Frew of NREL. And once again, there's no charge for this session, so you're all invited to attend that as well. Further information for registration is on our ESIG website. I think it might be on the screen here. If not, it's www.esig.energy. But once again, I'll thank the panelists and I thank everyone for their participation today. And once again, stay safe. So thank you very much.